Hi, and welcome back to another episode of Next Gen Ed. I have another pulley problem, so hopefully this is the last pulley problem. I think it will be. We'll move on to something else, but this has no pulley, technically. It's actually a tree, so obviously, and it's just this branch right here. So the rope goes around the branch, hence pulley-ish. So yeah, it's basically an angled pulley, so we really need to touch base with that because we've done pulleys where they go like one way and then they go back and something like that, but this is like this direction and then there's going that way as well. So yeah, so there's a little bit more to it than in the end, but it's the same concept, same principle. So we're given the length of rope and it's going to stay constant. So with this problem, so it says calculate the speed and time it takes to lift the wood 1 meter from the tree branch. So, and I say 1 meter because we don't want it to break the tree branch. Yeah, so you've probably noticed I do not do any prompts really. So I try to stick more with just like L equals this, and like it's just very straightforward, and like all these words can just confuse, and just the English can just really confuse some students. I'd say I'd really get in the habit of being like, hey, well, like 1 meter, so then measure YB this direction. So I'll put down right now then. So it's YB. So that's got to be 1 meter then in the end. So 1 meter is probably like this. 1 meter. So we want it to get to that point. So obviously he's going to be way out here. But for, I guess, math and educational purposes, like I don't want to draw all day. I have to have some room to do some math. Obviously, I've kind of made this drawing take up the whole stinking screen. Anyway, so I digress. So back to this. So yeah, like if you read this question right here, this little prompt portion that says 1 meter, so I'd recommend just saying like YB equals 1. So we're going to want to make it equal that. Technically, Y is a variable in the end. Yeah, so we're going to keep it as a variable for most of the time, but because we might have to take some derivatives and everything. So, but yeah, I would always recommend, like when you're doing starting off with a problem, you should just read the problem and then just take out everything that you can from the problem and just write it down. You know, L equals this, A equals this, Y equals this. That way you just kind of get it organized at the beginning, and then yeah, make sure your units are correct as well. You know, meters, seconds. Just try to make them very standard-ish. That's kind of why I don't use really full sentences. At least I haven't until like now. At least I don't think I have. But yeah, it's just an extra step. I'm not trying to include some English into my videos as well. So I'm trying to focus more on math and science and less on grammar, obviously. Physics is fun. They teach it so right. Okay, well, anyways, so we're going to move forward with this. We're going to basically figure out the speed and the time. So we put down VB, question mark, and then T, question mark. Basically, you're going to be at this YB. So another thing to note is that this length is going to be the whole length of the rope, obviously. Basically, it's going to be able to go all the way from the ground over to back to the ground. So technically, this will be the ground right below it. So this whole length right here, this whole length, that's got to be 4 meters. Just flat. So it has to be 4 meters. If this is 8, it's just half. So so the triangle is always like that. And we'll say that there's like some slack with the rope too, I guess. So obviously he's not going to always hold it like that. But in the end we'll have like put like a pin down somewhere, like a stake, and tie it down. But just for educational purposes, we'll just say like this is, he's just pulling it and it's in that direction. So nothing too complicated then. For the most part, this is just always going to be 4, and then we're going to have basically, let's extend that, pretend that there is extra rope. That's going to be XB, well, not XB, XA. So A is the guy, B is the wood. So he's going to be heading in that direction. So basically that's our whole setup so far. Just to start off then, we're going to have our equations. I'm just going to write them kind of in the tree because I do not have room. And I'm not going to erase them anyways. So it's kind of convenient to put them in the tree then. So S, basically that's going to be this side. S, that's going to equal the square root, so it's Pythagorean theorem again, so it's going to be XA squared plus, and that's going to be 16, just because it's 4 on this side, so 4 on that side, and then it's XA is the distance that he's traveled. So he starts from the beginning, you know, where it's 4 meters over there and 4 meters over there, and he just grabs the rope and he starts walking that direction at this acceleration, 0.12. So yeah, so pretty much our triangle that we're making from it in the end. That's our formula using Pythagorean theorem. So, and then we're also going to have basically our length formula. So what we normally used to doing in the end. So it's going to be L equals, obviously, and then the length is just going to be YB. So we have this length, right, you know, obviously. So, and then it's going to be S completely, because, you know, we're pretending there's more slack here, you know, for when he's pulling. So, and plus S. So that's going to give you your length in the end. And we know our length is just 8. It just stays at that amount. So it's just going to be 8 equals all that stuff. So yeah, so now let's get our equation in terms of YB. That equals 8 minus S. So then YB equals 8 minus the square root of, well, let's put that guy in there, you know. So XA squared plus 16. Boom. So now we're going to get our velocity equation. We need to get that in the end. So, see, we're going to do VB equals, so we take the derivative of 8, that's going to be a 0. Take the derivative of this, well, this is the same thing as like 8 minus, so obviously we got the beginning part, then XA squared plus 16 to the 1/2. So since it's to the 1/2, it is going to be, you know, times by 1/2, so it pulls it out, you know. So basically we're going to have a 2 in the denominator. So just because it's 1/2, you know, 1, 2, so 1/2. So then we're subtracting 1 to that, so then we get negative 1/2. So if it's negative 1/2, that's just a square root, but in the denominator of that. So we just literally take that, put in this denominator as a square root. C squared plus 16. And then the numerator is just going to have the chain rule to it all, you know, and we still have the negative sign there, so obviously that's just on the outside. So there's going to be 2XA, so because the power comes out for it, you know, and just like we did with the 1/2. And this can be times by VA though, just because we have to take the derivative, so we have to do the chain rule, so we have to do the velocity in terms of A. So And in the end, that just cleans up 2, so 2's cancel. And then guess what? Boom, that is S. So S is the denominator in there, so it turns out to be negative XA times by VA. That's going to be over S. Boom. So we got to find S, we got to find XA, we got to find VA in order to get VB, so the velocity that it's headed. So S is then going to equal, so if this side is 1, then obviously there's got to be 7 meters of rope on the other side. So then I should put it right here, plus 7 meters. So we're going to use that information, then we're going to be able to, I guess, solve for XA. So we're going to be able to get XA, because when you get XA, you got to get VA. So we'll just put that in our list over here. VA, just helps us get VB in the end, both of those. But yeah, let's move forward. So we're going to have 7, and then since we're using this whole thing right here, we're just going to square it. So, because it's like c squared. So c squared equals, and then xa squared plus 16, And so that's 49. 49 plus, minus 16. So that gives you 33. So xa squared equals 33. So xa equals the square root of 33. So, and then that's in meters, obviously. So I just write that down just to record it. So xa equals the square root of 33 meters. And then now we have to get VA as well. So if we're given our acceleration of the man, so we just got to do the integral then. So AA equals 0.12. So it's meters per second squared. I just won't include that. So then we have VA. So when we integrate, we get, basically it's a constant, so it's a constant times by t then. So it's 0.12 t. So also to note, I try to draw my t's with a little curl, so just so they're a little different from plus signs. I have horrible handwriting, so I'm working with it. So, but anyways, so that's going to be plus c, obviously, when you integrate. C is just 0, so we're just going to say he starts from rest, So he's not running and grabs the rope. That's very ill-advised, obviously. So, but yeah, so we're just going to ignore that, and it is just this in the end. And when we integrate again, draw our arrowhead. So then we're going to xa is going to equal, so then it's going to be a 2, and then we have to divide by 2. So then that turns into 0.06 t squared. When you take the derivative, 2 comes out, opposite of it. So that's going to be plus c again, obviously, but we're going to say this is our x naught. So we're just going to say that is 0 again. 0. Okay. So now with that in mind, we're able to calculate time as well, because we're given that. So let me just write that equation down real quick. So, okay, now that we got all cleaned up, we're back at it. So we got the equation VB over here. So, and then we have our equations for VA and XA, just from our acceleration and everything. So we're going to continue forward, and then we obviously still have the XA amount, so we're going to use that right this instant. So that's going to equal, so that's XA, I should say XA equals that, so then that's going to equal 0.06 t squared. So we're going to solve for t now. So t squared equals the square root of 33 over 0.06, and then bust out our trusty calculator. I hate how it turns off. I'm like, this is a computer program, just stay on. So ignore this. Oh no. Second quit. There we go. So we're gonna have the square root of 33, and then that's gonna be over. What is it? 0.6. We gotta take the square root of all that in the end. 0.06. Enter. We gotta take the square root of that. Okay. So it's 95.74 and then 99.78. And therefore t equals, actually let me just write that over here. That's one of our answers. T equals 9.78. That's in seconds, so that's our first one. So it's going to take him about 10 seconds to get all the way over there, so I guess he's pretty heavy, or I don't know, maybe he's just doing it in a very lazy, cautious way, I don't know. So taking him some time, so we have that, so we have T, and now we're able to get VA though. So, and we already have XA, obviously, so just filling in all the gaps. So VA is then going to equal, so 0.12 times by T, and then so our time is 9.87, so 0.12, 9.78, sorry, I said that wrong, but whatever. You know what I mean. So, get our calculator out again. 0.12 times by 9.78. So that's 1.17. Not too bad. So it's kind of flying up there, but not that fast in the end. Should be fine in the end. So 0.17. So VA equals 1.17 meters per second. So boom, there we go. Now we're able to implement all that into there and get VB. So then that's negative the square root of 33. That's by 1.17. All that over just 7. Is that length? Get our calculator out again. Times that by the square root of 33. Divide that by 7. We're good to go now. So it's 0.963. So, and I'm going to leave it as positive. I know it says negative right here. However, basically it's saying that it's shrinking, this vector right here. So the vector is shrinking itself from a larger arrow to a shorter arrow. That means the wood is going up. So let's just leave it positive, okay? So we're going to leave that portion as positive. So it's 0.96. That's good enough. 0.96. So VB equals 0.96 meters per second. Okay, so we got both of those, and that's pretty much it. However, kind of decided that I want to do a little bit more than this. Let's see if we're going to hit the tree branch even. So let's say, like, you know, after all this acceleration, it's just going to have that momentum and everything. So it's less about momentum though, it's more just it's going to have that velocity. So we're just going to use kinematics, simple kinematics, to see if it's going to hit the tree. So let me clean up real quick again. Okay, voila! Everything's cleaned up now. So moving forward, so we have VB equals 0.96. So basically it's just going to have an upward velocity at that point of that. So we're just going to say that's V naught for our kinematic equation. Y naught, so that's going to be completely different from this Y. It's just literally this kinematic equation in the end. Y naught for our equation, basically this equation, completely different from these Y's, is going to be so A Y, so that's T squared, a half y T squared minus plus V naught T plus Y naught. So with that equation, that's where we're getting this. The Y naught is going to equal, it's going to be 3. So if this whole distance is 4, if it's 1 meter from the top, it's going to start off at 3. So now if we make our equation, because A is just going to equal negative G, 9.81 meters per second squared. So then we get y of t equals 9.81 over 2 t squared plus 0.96 t plus 3. I think it's a little bit good to show how the calculator works though with this as well. So we'll do that to start off, at least. Our calculator turns on, our fake calculator. So that's going to turn out to be, so for this, I accidentally wrote this first one wrong. It's divided by 2. Okay, well, rewrite everything. I should have said insert, second insert. I'm a little rusty with this, but I'm getting there. So plus 3. So a positive velocity and a positive position. So in the graph, like that. So zoom out. Just back to that. Okay, and then we can go to max here on our calculator. So left bound, so just go left of the peak and press enter. Right down, go to the right of the peak. If we go there, there we go. Then press enter again, guesses, and ooh, so y is 3.0469. So that's great news. It's not going to hit the tree branch. So lucky us. So yeah, so that's how to do it with the calculator. I'll do it also with this. You can totally end the video at what you want. So I'll just overkill it though, like usual. So why not? So we'll get that number in the end. So it was like y max equals 3.0 something 4. That was a 4. Wanted to say that. Just didn't trust my judgment. Yeah, anyways, so let's take the derivative of this equation. Well, it's negative 9.81 t plus 0.96. So let's set that equal to 0 because the velocity in the y direction should be 0 at that point of time. You get t equals, so you subtract that to that side. Really, it's more like you add that to that side. Divide by 9.86 on both sides. So 96 over 9.81. Calculate. Meet more. 0.96 divided by 9.81. And again, this is a different time, so this will be added to the other time, this time over here, in order to get the total elapsed time of him pulling it to where it peaks. So a little different, but whatever. This time is just associated with this quadratic formula, this kinematic equation, I should say. They're both the same quadratic formula, kinematic. Yeah, well, one is mutually exclusive, but anyways. So 0.0997 8. Right? 8. Cool. And then we're just going to implement that into here, and then boom. So I'm not going to write that all out. Just know we're taking this number and we're putting it in there. So technically, we can even go to table and be lazy that way. And literally go, table set actually. So instead of going to auto, we go to ask. Second table. So we'll ask it this amount of time. So 0.098. It literally just computes it for you. So yeah, and that's what we calculated earlier. So cool. So again, so that's a way of doing it. Literally, if you have this equation here and you go to second table ask, it literally plugs in that number. So a little overkill, but let's finish it up. So second put. So we're taking this time amount and we're going to put it in the equation. So negative 9.81. We basically did this via the graph. And I guess, graph and calculating as well. So that's my second answer. Square that. Divide that by 2 plus 0.96 times by, oh, and we know the second answer. Let's just take the t value plus 3. Okay, so we got 3.047, just like we had before. So, boom, overkill to the max. Whoa, overkill. We found it 3 different ways, very much. So, but yeah, hopefully you enjoyed this little problem. Technically, it is more of a tree problem, not a pulley problem, but whatever. So, but yeah, also, don't mind my ugly tree. It's got like a turmeric tree branch. But yeah. Okay, well, I am out. Have a good good rest of your day, whatever day you watch this. But yeah, anyways, bye.